Welcome to Regents Chemistry Review. I'm Mr. Chille. What I have behind me is the first page of the notes that I'll be projecting onto this LCD screen. You should print out a copy of these notes, page for page. And also, you should have a copy of your reference tables with you. If not, you can go to the New York State website and print one out. Okay, let's get started. The first unit is called the physical behavior of matter. And of course, chemistry is the study of matter. And matter can be divided into two categories right away. And that is one, substances, and the other is mixtures. So they're not the same thing. Let's put a not equal sign here to remind you of that. Never refer to mixtures as substances. When it comes to substances, we're talking about elements and compounds. And if you open up to the middle of the reference table, to your periodic table, you'll have some symbols of elements that I'd like to include here. And that is Na, which you probably know by now is sodium. If not, you could always refer to table S, where you have the symbols of the elements listed there with their names and some properties. Another element would be H, hydrogen, O, oxygen, Cl for chlorine. And so there's over 100 elements. And then if you take these elements and you combine them chemically, you'll form compounds. I'm sure you all know of H2O, that's water, NaCl, which is sodium chloride. Another combination of these elements, H2O2, which is hydrogen peroxide. And clearly, H2O2 is not the same thing as H2O. So you can tell that these are compounds because we have the symbols of two or more elements side by side, and they're in specific ratios, and that's what these numbers here indicate, which are called subscripts. We'll talk more about formula writing much later on. And then for some examples of mixtures, where we physically combine these things, well, this grouping right here could represent a mixture, provided these elements don't react with each other. Another mixture might be taking the NaCl and the water together. NaCl slash H2O. So the sodium chloride dissolves in the water, and in fact, this mixture would be abbreviated by NaCl AQ, which indicates that sodium chloride dissolved in water gives us an aqueous solution. AQ here stands for aqueous. We'll talk more about that, the whole dissolving process in solutions, in a later unit. Okay, so since these notes are hooked up to my laptop and projected on this LCD, you'll have to bear with me as I erase these points. You could read on if you'd like, and then I'll just click down to get to you. Okay, speaking of elements, one thing you want to know about elements is that because they are the simplest kind of substances, elements can't be decomposed. They can't be broken down. I'm sure you've heard the expression, it's elementary, my dear Watson. That's what Sherlock Holmes used to say to his partner, because elements are so simple, as in elementary school. And then as far as elements are concerned, you should know this term here, allotrope. Allotropes are when you have the same element, but because there's a difference in structure, there will be difference in properties. Common examples of allotropes would be the allotropes of oxygen, O2, ozone O3. To illustrate the difference in structure, let's draw an oxygen molecule, two oxygen atoms with an equal sign, which represents a double bond. An ozone molecule would be three oxygen atoms on an angle, and you wouldn't have to know that by heart, but the point is that because they have a difference in structure, they'll have a difference in properties. And then more commonly tested are the allotropes of carbon, which would be diamond. So let's draw a diamond here, which maybe you didn't know consisted of just carbon, the tetrahedral arrangement. So this would represent the carbon atoms, very tightly packed, and that's what makes diamond such a hard substance. It's very hard. And on the other extreme, we would have graphite, which consists of layers of carbon atoms with strong bonds in between the carbons and the layers. But what holds one layer to another layer are these dispersion forces, which are very weak. And so it's very easy to separate these layers from each other. In fact, you would find graphite at the end of the number 2 pencil. And when you ride the pencil across the paper, you tear apart the dispersion forces. So graphite is very soft. And then the buckyballs, which is a nickname for the Buckminster fullerenes, would be balls of carbon. The main point being is because we have a difference in structure, we'll have a difference in properties, even though these three substances here consist solely of carbon. Okay, let's continue and focus on chemical versus physical. Some key words you want to know for physical changes and properties. Break, tear. When you break something, when you tear something, it's still the same substance even though you've changed its shape, its form, and that's what makes this a physical change. Other key words, when you melt or boil or dissolve things, these are all examples of physical changes or physical properties tested. The key is that it's still the same substance. So for example, when you take ice, H2O solid, ice, and you melt that ice into H2O liquid, which you and I would refer to as water. Clearly there's no new substance here. We've changed the state, but it's still H2O. So melting is an example of a physical change. And the melting point of a substance is a physical property. Turns out that the melting point of ice is 0 degrees Celsius. Now, as far as a chemical change or a property, some key words you ought to note is react. When you react something, when you chemically combine something, because you're forming new substances, you have a chemical change. Other key words, burn, tarnish, corrode, rust. In each of these cases, you're forming a new substance or substances, and hence you've tested a chemical property. So let's have water undergo a chemical change. Let's take H2O as a liquid, 2 parts water, and add some electricity to it. It's electric. And that breaks down then, as a result, into 2 parts hydrogen, which is a gas, and oxygen, which is a gas. Now, you may have forgotten how to balance, but we'll do that later. The point is that we end up here with new substances. These are new substances. And so this process of breaking water down into its elements would be an example of a chemical change. By the way, this process is called electrolysis. Electrolysis. Using electricity, electro, to split a compound, lysis. We'll talk more about that in the electrochemistry unit. Again, in the case of melting, H2O, end up with H2O, it's the same substance. In the case of electrolysis, in this example, H2O becoming H2 and O2, those are new substances, so this is a chemical change. You'll see any questions on this is just a matter of knowing the key words or noting in the example whether or not it's the same substance or different. Okay, let's continue. Now, if we want to contrast or compare and contrast compounds and mixtures, I would focus on, when it comes to compounds, we're talking about elements chemically combined. You might want to use the term bonded to each other. Because of a chemical reaction, the elements have been bonded to each other. And of course, if they are chemically combined, to break down a compound, you would need a chemical change. So chemically combined, chemically broken down. The compounds, as you can tell from their formulas, have the elements in definite proportions. So as I said before, H2O isn't H2O2. H2O would be referred to as pure water by some, or distilled water. As opposed to tap water, which would come from the faucet, or rainwater. Mixtures, on the other hand, are when you have elements and compounds, or compounds and compounds, or elements and elements physically combined. They're not bonded to each other. Therefore, they can be physically separated. Mixtures have indefinite proportions, which means it's totally up to the person making the mixture, the composition of that mixture. And so you'll see from sample to sample, there can be a change, they can vary. For example, let's compare Coca-Cola versus Pepsi-Cola. If you look in the back of a Coca-Cola can or a Pepsi can, you'll see a list of ingredients. Now, the amounts of each of those ingredients is totally up to the manufacturer. So Coca-Cola is generally sweeter, has more sugar than Pepsi-Cola. Pepsi-Cola, even though it contains carbonated water, just like Coca-Cola, some people say Pepsi-Cola has more fizz. So that's totally up to the manufacturer. This is a list of ingredients. Not one formula. Okay, when it comes to mixtures, you ought to know the difference between heterogeneous and homogeneous mixtures. So let's look at that. The illustration I have at the bottom of this page, oil and water versus salt water, will serve that point. When you look at a sample of oil and water, you can tell the oil apart from the water, because the oil doesn't dissolve in the water. Some people say they don't mix. Well, technically they do mix, but when they mix, because they look different, we would say that oil and water is a heterogeneous mixture. On the other hand, if we take salt and water, because the salt dissolves in the water, they look the same. They look like one. Since they look the same, we would say salt water is a homogeneous mixture. Or in one word, a solution. If you want to separate the components of a heterogeneous mixture from each other, as in the case of oil and water, you could use a filter. And the oil would get trapped in the filter and the water would pass through. Or if you had, let's say, a piece of iron in here, Fe, you could fish out that iron with a magnet. Or if you had a sample of dirt water, you could spin that sample of dirt water down and separate its components in a centrifuge, and the more dense components would end at the bottom of the test tube, and less dense components would be towards the top. So centrifugation is a separation based on density. Other examples of heterogeneous mixtures would be sand and water, because again, the sand doesn't dissolve in the water. Or rock, any rock. Obviously, when you look at a rock, you can make out its different components, its different minerals. If you want to separate the salt from the water, since a filter won't do, you're going to have to evaporate the water. So if you let this stand, the water is going to leave as a gas, and then you'll be left with a salt encrusted on the bottom of the test tube. If it's sodium chloride as the salt, because there are many salts, we represent it as NaCl solid, and the H2O leaving as a gas. Other methods, physical methods of separation for solutions would be distillation. Distillation is a separation based on boiling point, BP. For example, let's draw a distilling flask first of all. So round bottom, then you'd have something like that. Okay. What you would have here at the bottom is a solution of liquids with different boiling points. For example, let's take hexane, which is an organic solvent, and pentane, another organic solvent. And these dissolve very well in each other. They're miscible. We'll come across these terms later on, especially the organic. If you're weak in your organic, I have an extended unit on organic. So because these liquids have different boiling points, when you heat this up, a little fire there, cap on the distilling flask. What will happen is the pentane, which is the smaller of the two, will boil first. It has a smaller size molecule, and so it boils first. So when the pentane boils or vaporizes, those vapors rise and then pass through the condenser, and through the condenser they cool down and turn into a liquid. So you could separate these liquids from each other. Usually there's a thermometer in here, so you could track the temperature at which that liquid's boiling, since boiling point is a very important physical property. Another method of separating the components of a solution would be paper chromatography. Now the way this works is by a difference in solubility. Probably remember paper chromatography from junior high. I doubt you did it in high school. The standard experiment is to take a piece of filter paper and spot it with a mixture of pigments, colored pigments. For example, let's say black ink. Then when you place this filter paper, this strip, inside alcohol, ALC, what's going to happen is, as the alcohol is absorbed by the paper and passes through this spot, it's going to dissolve the different components of this black ink mixture to different degrees. And what you'll end up with is colored bands at the top of the paper, and the dye, which was most soluble in the alcohol, will go the furthest up the paper. So this one here would be the most soluble. Okay, as far as other examples of solutions, you should note, besides having a solid and a liquid, as in the case of salt and water, you can have a liquid and a liquid, like CH3OH in water. CH3OH is an alcohol. It's known as methanol. Another one would be C2H5OH, ethanol in water. You should memorize these two alcohols because they're so common. And again, we'll cover this in the organic unit. Or you could have a gaseous solution, as in the case of air. Nitrogen, oxygen, and water, and of course other components are found in air. This is in order from most to least, is a gaseous solution. And then you have Solid solutions. Now it's hard to picture two solids dissolving in each other, so what happens here, as in the case of brass, which consists of zinc and copper, what they do is they melt both solids, mix them together, and then when they solidify, you can't tell them apart. 14-karat gold is another example. That's not pure gold. They add the copper to the gold to make it harder. And here is an example of steel. You could have carbon and iron. These are all examples, by the way, of alloys, which are solid solutions that contain at least one metal. Okay, that's pretty much it for the first page. You could stop here if you'd like. I'm going to stop the recording here. You take a break. That's the beauty of this presentation. You can stop at any point or replay it. But I'm going to move on to page 2. So I'll see you there.